Okay. Thank you, René. Hello, everyone. Okay, so welcome to this presentation about the vibrating wire piezometer. Today I'm going to use a presentation that I gave to a group of people last month. A group of people who were users, very much interested in knowing about how to use and install vibrating wire piezometers. So this presentation will focus quite a lot on these technical aspects. Okay, so my presentation will be divided as follows. I will give a definition of the piezometer and give the typical applications. I will talk about the main types of piezometers available. I will describe briefly the vibrating wire technology, and I will describe more in details the vibrating wire piezometers. And finally, the two most important sections will be about how to read the piezometers and how to install them. And also some sales documents will be presented. Okay, first, what is a piezometer? A piezometer is a device that allows to measure the pore water pressure at a fixed point into the ground. It is really important to understand that the piezometer must measure the water pressure at a certain elevation into the ground and should not be affected by what's happening above or below. The typical applications can be divided in two. The first one is when we are interested in monitoring a pattern of water flow. A typical example of that is for dam monitoring. We will install, it will be common to install piezometers in the dam and in the dam foundation to determine what is the water flow through the dams and below it, to validate that the dam is behaving a good way, a proper way. The second application is for determining the soil effective strength. This is really important to do that because the soil effective strength is directly related to the pore pressure in the ground. So, for instance, when you are building an embankment, and as the fields are placed, it is and compacted, this compaction process will increase significantly the pore pressure into the ground, which will in return decrease the soil strength, the effective strength, which can be dangerous for this can cause soil failure in the embankment. So it is really important to measure the pore pressures in that situation. So these are two examples of the two most important applications. Okay, now the different types of piezometers. 100 years ago, or around 100 years ago, the people were using what is called a standpipe piezometer or a Casagrande piezometer. This piezometer consists of a pipe at which you have at one end, at the bottom end, there's a filter that will allow the water to get in the piezometer, but not the soil. So only the water will get through the filter and will go up in the pipe. And so by measuring the water level in the pipe, it will be possible to know the exact water pressure at the elevation of the filter. You will note that it's important in that case, the installation is really important. It's important to isolate the zone where we want to measure the pore pressure. And we do that normally by making a plug just above the filter. And this plug
normally consist of bentonite, of bentonite. The bentonite is a type of clay that has this special characteristic or special features of swelling a lot when it's filled when in contact with water. So it will create a perfect plot. Over the years, different types of piezometers were developed, and most of them were work under the principle of the diaphragm piezometer. A diaphragm piezometer is a piezometer in which there's a diaphragm, and the water will get inside of the piezometer, and it will the water pressure will act directly against this diaphragm. And by measuring the deformation of the diaphragm, you will know what is the water pressure. So many piezometers were developed following this principle, including the pneumatic piezometer and the vibrating wire piezometers. This type, the diaphragm piezometers, are really interesting compared to the standpipe piezometers because it's possible to have automatic data acquisition, and also because the time lag is much more smaller than with the standpipe piezometer. That's a problem with the standpipe piezometer. You need a larger flow of water to in order to be able to measure a variation of pressure, because you have to fill this pipe. So this in clayey soil, for instance, this can take quite a long time. We can have to wait for hours or days before seeing any change in pressure that will result in a change in elevation in the pipe of the standpipe piezometer. Okay, now a few words about the vibrating wire technology. The vibrating wire technology was developed in France in the 30s by a French engineer, Mr. André Cohen, who got a patent and developed instruments for measuring deformation or extension in dams, for instance. So he developed these sensors and installed them in a few dams in France in the 30s. And quite rapidly, this new technology became very appreciated in the civil engineering field. And the reason for that is that the people realized that this technology is well suited for the difficult environment conditions that can be encountered in this field. And more specifically, an interesting feature of this technology is that it can give stable and accurate results over a very long lifespan, a long time. And actually, many of the first sensors that were installed in the 30s in France are still working properly. So it shows that that's an interesting feature, because as you know, when you embed or install a sensor in concrete or inside of the dam, you wish the sensor to work for a long time. You don't want to be forced to replace it every 5 years or 10 years. So ideally, you will wish that the sensor will last as long as the structure itself. So the vibrating wire technology is appreciated for that. And also it is appreciated from the fact that the output, the signal output that is obtained with such sensors is a frequency, which is interesting because it makes this type of sensor less affected by the length of the cable or any potential faults in the cable. So with the vibrating wire sensor, it's possible to use cables that will have up to 1 or 2 kilometers, and it will be possible to change the length of the cable over the years without affecting the value of the reading that you obtain from the sensor. So this is very important. This feature is really appreciated. So over the years, many manufacturers developed different type of sensors based using this technology, including Telemac, that was founded in '47 by Mr. André Cohen, and Iron Gauge, that was founded in 1973. Roctest gained a lot of experience by purchasing these two companies. Indeed, Roctest purchased Telemac in '91, I think, and Iron Gauge in 1988. So thanks to these two companies, Roctest has a long experience with the vibrating wire sensor. Now, the principle. A vibrating wire sensor consists of a steel wire, similar to a piano wire, that is connected, fixed to two anchors or two mounting clamps. And any change in distance between these two clamps will affect the tension in the wire. So by measuring the resonant frequency of the vibration of the wire, it will be possible to know if there's any change in distance between these two clamps. For measuring this frequency, it is necessary to install a coil very close to the wire. And this coil, either one or two coils, will be installed, and they will excite the wire. They will make it vibrate, and also these coils will be used for reading the frequency of vibration of this wire. So that's the basic principle. Now, the relationship between the frequency, the vibration frequency, and the distance, or the change in distance between the two clamps is the following, is the one that you see. You will note that this relationship is affected by L, the length of the wire, P, the volumetric weight of the wire, and E, the Young's modulus of the wire. So L, the distance between the two end clamps, will be different depending on the type of sensor that you are using. This is the typical relationship. This is the relationship between the frequency and the distance between the two clamps. Now, there are three ways of reading a vibrating wire sensor. The first one is the pluck and read method. The second one, the sustain method, and the third one, the auto resonance method. The pluck and read method is the most common method. This is the method that is followed by all North American manufacturers of piezometers, of vibrating wire piezometers. With this method, you have two coils that are connected together with two wires, and both coils will be used at one moment for exciting the wire, and then the same coils and the same circuit will be used for reading the vibration. This is the pluck and read method. The second method is the sustain method, and this is the method followed by the Telemac sensors. In that case, the two coils are separated. Both are connected to two wires each,
And so you have two independent circuits. One coil or one circuit will be used to always excite the wire, and the other one will be used to read the vibrations in the wire. So this can be done at the same time and in a continuous way. And finally, the last method, the autoresonant. This is not very common. This is the Geonor gauge manufactured in Norway that are based on this principle. In that case, the sensor itself will include small electronic circuits that will be connected to the coil. So I won't talk much about this method because it's not a common method here. This slide presents with more details how the plug and read method works. I will let you read it by yourself. It has some interest, but it goes. It goes and gives some details that you can read by yourself. Now, I will give more details about I will describe with more details a vibrating wire piezometer. A vibrating wire piezometer consists, at the right you can see that there's a filter. So at one end there's a filter that will allow the water to get in the piezometer, and the water will fill a cavity here and the water there will be in contact with the diaphragm. So any pressure change will result in a change, will deform the diaphragm. Then you have what we call the sensing element or the insert here. And this part here is the part containing the vibrating wire. The vibrating wire is connected at one end to the diaphragm, and it is anchored at the other end to the sensing element. So this wire, the wire will measure any deformation in the diaphragm. Then you can see on that picture, on that drawing, that there's a gas tube surge arrestor. This is for giving some protection against surge, electrical surge. What is important to know is that if these type of sensors, one important threat of these sensors are the lightnings. So we try to give some protection to so this is why you can see a surge arrestor there. Then you can see that there's a thermistor. There's a temperature sensor in every vibrating wire piezometer. This is necessary because the reading obtained from a vibrating wire piezometer is affected by temperature. So by measuring the temperature, it's possible to make a correction for temperature change. And then you can see the wires are going through the connectors to the electrical cable, which goes to the readout box. So typically, a vibrating wire piezometer looks like this. Now, the vibrating wire piezometers can take different shapes depending on the application. The standard piezometer is the first one at the top. This is equivalent to our PWS piezometer. And this piezometer is designed for being installed in boreholes. The second type that you can see from the top is the PWC, which is equivalent to the PWS, except that the filter has been replaced by threads that allows to connect this gauge to a pipe. And actually, this is not really a piezometer; it's more a pressure transducer in that case. But we don't sell a lot of PWC. This is not. The third example is the thick wall piezometer. This piezometer is designed for installation in embankments. It is equivalent to the PWS, with the exception that the body or walls are much more thicker, which allow this type of piezometer to sustain a large earth pressure without any deformation of the body and without any effect on the reading. So this is why when users wants to install a piezometer in large embankments or large dams, they will choose this type of piezometer. And finally, you can see the PWP, which is the push in type of piezometer that is characterized by having a conical points for pushing it into soft soil. And at the other end, you will note that there are threads that allows the connection of pushing rods. Okay, now here are the typical specifications of the vibrating wire piezometers. First, you can see the range. You can see that the range can go, in that case, can go from 35 kPa to 7,000 kPa. And then you have the accuracy. The accuracy is obtained from a calibration. Every piezometers are calibrated here in the factory. So this calibration consists in applying a known pressure steps to the piezometer and simply reads the piezometer. And from these readings, we can deduct or obtain a tendency curve that we can obtain by doing either a linear regression or a polynomial regression. With the polynomial regression, the error obtained, the maximum error will be smaller. And this is what we call here the accuracy. The linearity shown just below is the maximum error that you will obtain if you use the linear regression. So as you can see, the maximum error is a little bit higher. You will note that the linearity is expressed in terms of percentage full scale. And it should be the same for the accuracy. That's an error on this slide. It's, the accuracy should read 0.1% full scale. So the error is related to the range. So which means that, for instance, that if you select a 200 kPa range piezometer, the accuracy being 0.1% full scale, this means that the maximum absolute error will be 0.2 kPa. But if you select 1000 range piezometer, the maximum error will be 0.1% of 1000, which is 1 kPa. So when you select a range, when someone is selecting a range for a piezometer, it's important to select a range that will be large enough for the expected application, but at the same time, on the other hand, it should not be too large for nothing, because you will increase the error that will be obtained from the readings. Then you can see the resolution that is given, which is quite similar to the sensitivity, which is the smallest increment that you can detect from a reading and the smaller change of pressure that you can read. And then you can see the thermal drift value. The thermal drift value here is 0.1% full scale per degree C. This means that if the temperature change, if there's a 10 degree C change, you will this will result in a 1% full scale change. So as I mentioned just before, you
can see that the piezometers can be affected by temperature change. So it is important to monitor temperature as well as pressure with the piezometer. Then you have some information about the temperature sensor included in the piezometer. In our case, we use a 3 kilo ohm thermistor. Then you have the different type of cables that are available. And finally, you can see the different models and different sizes of each model. And which brings me to talk a little bit about the PWL. The PWL is a low-range piezometer. You will note that the dimension, the diameter is large. It's quite large because in order to get accurate results in the low range, it is necessary to have a larger diaphragm. This way you get more, the results are more, the readings are more accurate. So this type of piezometer has a larger diameter. This type of piezometer is also characterized by the fact that it needs to be vented because it is important to note that our piezometers are absolute piezometers. We'll give an absolute reading of both the water pressure and the barometric pressure change. And this is the case because the sensing elements, the insert is sealed. There's a vacuum in there. And so when you look at the diaphragm on one side, it is open to atmosphere, but not on the other side. But this configuration is not good when you go in the lower range because the effect of barometric change becomes important compared to the readings. So it is necessary to vent these type of sensors, which means that you need a vent tube that will reconnect the sensor to the surface. And this vent tube is a small plastic tube that is located in the electrical cable. This vent tube also, at the end, you will have what desiccant included in the cartridge, and this desiccant must be changed periodically. And the role of that is for preventing of any humidity ingress or infiltration through the wire, through the tube, which would damage the sensor. So this type of sensor, the PWL, is not very. We don't sell a lot of PWL because this configuration is not so convenient. It requires more maintenance. It's quite expensive too. So, but it is available. It's there. Then you will note that the material of the piezometer is stainless steel. And this is easy to understand because you want the piezometer to last for a long time in water. So this is why a piezometer is made from stainless steel. Then you have the filters. You have two different types of filters. The standard type is the stainless steel type. This type of filter has the permeability, it's more permeable. The water will get in more easily than the ceramic filter. And you can see that by the pore dimension, the pores dimension, which are about 50 microns compared to about 1 microns with the ceramic filter. So the ceramic filter, they won't let the water in easily. They are not permeable. This type of sensor of a filter, the ceramic filter, was developed because over the years it was noted that in fine material, in clay soil, that there was a possibility of fine migrations to the filter that would plug the filter. So the standard type of filter is the stainless steel type of filter. But if someone is installing a piezometer in clay, they might consider using a ceramic filter. There are some important features that have been outlined there with the red arrows. You can see first that the ceramic filter will allow to measure suction, will allow to measure negative pressure down to about minus 100 kPa. The stainless steel filter cannot do that because it will desaturate quickly. And once it's desaturated, the readings won't be good anymore. You will have to wait for the filter to resaturate, and then it will start again to give good readings. Another important feature about the ceramic filter is that it has a much more important time lag. With the stainless steel filter, the time lag is just a few seconds, or 10 seconds, 15 seconds, not more than that. Whereas with the ceramic filter, the time lag can be hours. And, so this is an important feature. Okay, now the reading, how to read a piezometer, a vibrating wire piezometer. What's important to keep in mind is that a vibrating, the output from a vibrating wire piezometer is a frequency. So you get either a frequency in hertz or a period in microseconds. One problem related to that is that the relationship between the reading, the raw reading, the frequency, and the phenomenon that we are measuring, which is either a pressure change or deformation, is not a linear relation. As you can see, the F is of the second order here. So it is more convenient to work with what we call the linear units. The linear units, also called digits by other manufacturers, are equivalent to the microstrains of the tension wire in the piezometer. So that's why we will use a conversion formula, which you can see here, formula here, for converting the hertz into linear units. And then we will work using the linear units. And as mentioned before, the K factor, which is the gauge factor, or which is equivalent to this factor here, is specific to the type of sensor. And in the case of the Roctest piezometer, this K factor equals to 1.1056. So depending on the type of readout unit you are using, you will obtain either directly a frequency or a period in microsecond, or some readout will give square hertz. Oops, I'm sorry. Will give the square hertz over 1,000 as a unit. This is the unit that will be displayed. And other readout will directly display the LU, the linear unit readings. So in that case, it is important when you are using a readout unit to select the proper position. Normally, the readout units will have a different position that will allow to read different type of vibrating wire sensor. And each position will be characterized, will be assigned one a specific gauge constant, and also a specific range, a frequency range that will be suited to the type of sensor that is read. For instance, with the PWS, the PWS is designed for working within 1,000 and about 2,300 hertz. So the position selected should be should cover this range. If you do not select the proper position, which has a different range, you might exceed you won't be able necessarily to fit into the range of the piezometer, and it won't be possible to take some readings. This brings me to talk about the compatibility between the different piezometers from different manufacturers. It is good to know that most of the piezometers manufactured by North American piezometers, vibrating wire piezometers, are compatible, or they are interchangeable. This means that you can use, normally you can use a readout unit from Roctest for reading geocom piezometers or slope indicator piezometers. And it's true, you can use also a slope indicator readout unit for reading an RST piezometers. This is normally true if we are talking about plug and read type of sensor, and also if you make the follow adjustments, because you have to take into consideration that each sensor has its own gauge constant, and the gauge constant from the Roctest piezometer is 1.0156, but the one from Geocom is 1. So there are some adjustments that must be made there. And also you must be careful when you select a position on a readout box, because you must select a position that will cover the entire range of the type of sensor that you are trying to read. But normally with the proper adjustment, it's possible to make these sensors there's a compatibility between the different type of from different manufacturers. Okay. Now, once you got the linear unit from the readout box, you have to convert that into pressure. And for doing that, you will refer to the calibration data sheets. On the calibration data sheet, each piezometer is provided with its own calibration data sheet, with its own calibration conversion factor. These conversion factors are the CF, the A, and B that you see on these two formula. And you can see that there are two formulas because, as I mentioned earlier, you can use either a linear regression or a polynomial regression. So from the L reading, you will use these formula and you will be able to obtain the pressure values. Then these pressure values will need to be corrected for the temperature change, if any, and also for the barometric changes. So this will be done using the CT, which is the thermal coefficient factor that is given on the calibration data sheet, and also by measuring each time you take a pressure measure from a piezometer, you have to take a barometric reading too. And this barometric pressure reading is taken using either a barometer, or you can refer to the some weather station websites to know the barometric pressure at the time of reading using the internet, or you can call also a local airport. You will get the barometric pressure at the time of reading. Okay, now the installation of the piezometers. The installation, there are different ways of installing the piezometers, and and I will describe the main methods for doing that. And before installing a piezometer, there are some preparation steps. First step is to take a reading at reception. When the client receives a piezometer from us, he must read it at zero pressure and make sure that the initial reading is close to the readings, the initial zero reading appearing on the calibration sheet. The next step is to install the filter. The filter will be installed this way. You have first to put the piezometer and the filter in a bucket filled with water. And then you will simply put the piezometer in place you will put the filter in place on the piezometer. If the filter, like the ceramic filter, is already in place, you have to remove it from the piezometer and then make sure that the water got into the piezometer and that there's no air bubbles, and you put the filter back in place. With the ceramic filter, when you are doing that, you need to take readings of the piezometer. The reason for that is that since the ceramic filter is not very much permeable, when you will push it in place, this will increase the pressure inside of the piezometer. So you will need to make sure that this pressure is not reaching dangerous level. It should not be higher than the range of the piezometer. Otherwise, there are risks of deforming or damaging the diaphragm. So this needs to be done. And finally, the last preparation step is to take the initial readings before installing the piezometer in the borehole or in the field. This initial reading is the zero reading, and all subsequent readings will be compared to this initial reading. So this must be done as shown by holding the piezometer in the bucket, and by making sure that by taking 3 readings, taking the average of these 3 readings, and this must be done while the water is stable in temperature. On this graph, you will see the summary of the steps that I've just mentioned. At the left, you see the first step is when the gauge is calibrated here at factory, and then you can see at reception you have to take a reading here, and the pressure should be about the same than during calibration. And then there's the filter installation step. I'm sorry for that. You can see that when you install the filter with the ceramic filter, you can see on the dotted line that the pressure changes are very small. But on the plain line, when using a ceramic filter, you will see that there are important pressure increase, which are shown here by a decrease in the linear units. And once the filter has been installed, it is important to wait for this pressure that was created into the piezometer to dissipate before taking the initial readings. You will note that this dissipation is quick, the stainless steel filter, less than 1 hour, but can take at least 24 hours when you are using a ceramic filter. So it means that you need to wait at least a day before taking the initial reading after having installed the filter. Okay. Now, the first type of installation is what you can see on this slide is the push-in piezometer. You can see on this slide simply that a pilot hole was done, and then the piezometer was connected to rods, and then using the drill rig, we simply push the piezometer to the appropriate level. On this slide here, you can see some pictures taken while doing the installation in an embankment. This installation is quite easy. You install the piezometer in a small trench. You can put it in a canvas bag, that we call it. But it's not. It depends on the type of soil in which you are installing the piezometer. And at the right side picture, you can see the cable. There are some loop in the cable. The way the cable is installed in embankment or in dams is really important. It is important to put some slack in the cable, because the cable should not be damaged in the future by any movement during construction that can happen, that can occur you can have differential settlement. So this is why it is important to take care or take some precautions when you are laying the cable in place. The piezometer can also be installed directly in the standpipe, as shown on the left side drawing. In that case, it will be possible to validate the reading obtained from the piezometer, the vibrating wire piezometer, by measuring also the water level in the standpipe. So you can use a water level indicator for that. Low-range piezometer can also be installed in Weir or small reservoir, as shown at the right. You may note that a vented cable is required in that case. Okay, these pictures show standpipe installation in standpipe. And finally, the method, the installation in a borehole. The installation in the borehole is more difficult. The traditional method consists, as I mentioned quickly earlier, to isolate the zone where the piezometer is installed. So you need to make bentonite plug just above it and sometimes just below it. And this installation is not easy. Because it is time consuming. You will need, for making the bentonite plug, you need to use bentonite pellets or bentonite chips, as the one that you can see here, and to drop them slowly by hand and to measure the level. And you'll have to wait, and it takes time. It takes time, and it's risky. Because if you go too quickly, the bentonite will get stuck too high between the cable and the casing, resulting in big problems. So this type of installation is not easy. So as mentioned here on this slide, the inconvenience of this what is called the traditional method of installing the piezometer in boreholes. This method is time-consuming, difficult to perform, and only a limited number of Piezos can be installed in a single borehole. The important advantage is that when it's properly done, it gives good readings. A new method of installation in borehole was developed over the last years, and it's called the Fully-Grout method. This method consists of grouting entirely the borehole. So you don't have to be careful to put sand at some elevation where the piezometer is, and then to install the bentonite, and then to fill the rest of the borehole with filling material. You don't have to do all these steps. You just put the piezometer in the borehole and you completely fill the borehole with the grouts. This method is, up to now, it seems to give good readings. It's much faster, it's much easier to install. The installation is much easier. And you can install more piezometer in a single borehole. The inconvenience up to now are not so clear. This method is quite new. We don't have a lot of feedback from this method, but all the feedbacks we get are positive, are good. But still, there are some doubts. There might be some problems coming from the fact that this Fully-Grout method increase a little bit the time lag of the piezometer. But it should not, it's not the increase. We would talk about maybe 10 minutes, 12 minutes of increase. So normally it's not, this additional time lag is not so significant for traditional applications. But for some application, from the pumping test application, it might be more a problem. So, but we still need this, the people still need to make some tests with this new method and to gather more information. Also, another inconvenience is the thinner layer that you can monitor using this method is not so clear. It might be about 1 meter. This is not so clear up to now, but we'll get normally this question marks are not so. It's not a big problem for the traditional or the standard application for the piezometers. Okay, so just as I mentioned, this method consists in grouting the entire borehole, and the grout we use is a cement bentonite grout. The piezometers must be installed with the tip upwards. So the piezometers can be simply tied to the electrical cable, or the more common way is to attach the piezometers upwards to attach them to the grouting pipe. The selection of the mix, the grout mix, is important. As you can see on the table at the right, normally you will try to select a mix of grouts that will be close to the type of soil that you are using. So the permeability and the stiffness of the grout you will try to match the one from the soil just around the piezometer. Okay, this picture was taken from a job that we did during installation of piezometers following the Fully-Grout method. We were at a dam construction site in northern Quebec, where we installed where 2 piezometers were installed in each borehole, and we were using H casing, and you can see that the piezometer was simply taped using duct tape to a 1.5-inch PVC pipe, the grouting pipe. The installation was really easy and quick. So we didn't have any problem. As I mentioned, one advantage of this method is that now it's possible to install more piezometers in the same borehole. You can install one in a 2-inch borehole, 2 in a 3-inch borehole, 4 in a 4-inch boreholes. And even more than that, if you use the new type of piezometers that were developed by manufacturers recently, which are the multi-level piezometer string. These piezometer string basically they normally consist of a large multi-conductor to which are attached various piezometers at specific spacings. So with this type of instrument, it's possible to install much more piezometers in a single borehole. Okay, now you can see on this picture a vibrating wire readout box, and use that is connected to a switching box to where to which many piezometers are connected. So you can see that there's a rotary switch, and it's possible to select different piezometers and take a reading that way. On this slide, you can see that from the piezometer itself up to the data acquisition system, there can be a quite complex connection system, which can include a junction box and also a lot of lightning protection devices. You will see that at various places the wires are grounded using rods installed into the ground. So the installation of a piezometer can be quite complex depending on the situation. Okay, so as a conclusion, I can say that the vibrating wire piezometers are a very important instrument for geotechnical application. This is possibly one of our most important products at Roctest. It is important, we may note that there are different ways of installing piezometers, there are different applications, different types of piezometers, and the way to read the piezometers, the vibrating wire piezometers, is not so easy. Proper preparation and training is quite important for the users to ensure successful reading. And finally, we can say that the new Fully-Grout installation method is a kind of a breakthrough or an important improvement with the vibrating wire piezometers, because now the installation is easier, is quicker, and it's possible to install more piezometers in the same borehole. And a few slides were recently added to this presentation, and I will present them quickly. First, you can see some useful links to very important documents that you can use for having more information about piezometers. You can refer to, you can consult the P lists that have the following address there. This presentation is also available at this address, and you will find papers about vibrating wire piezometers, this address. The data sheets and the instruction manuals are also available, and the instruction manuals, among others, constitute a useful tool. A lot of information is included in the instruction manual. There are some reference. I don't know if I see them. Okay, here. Also on our network, you will find references of jobs or related to products that can be very useful to you. But as mentioned earlier, Roctest has been involved with selling vibrating wire piezometers for a long time, so we have a lot of references. We are probably the company, including Telemac and Aerogauge, the company who has provided most important numbers of vibrating wire piezometers that are installed today in dams. And there are a few comments that were added, and most of these comments I've mentioned that in my presentation, but I will let you consult that by yourself. Yeah, I think that I covered all these items. Okay, no, yeah, okay. Now one comment there maybe that the installation of the PWP is something that can be difficult. They should not be driven, or hammering should not be used. They should be pushed in place if you don't want to create any important offset or even to damage them. This type of installation is difficult because the results are not guaranteed. Sometimes there will be some problem. If you, for instance, if you leave the rod in place and soft material, sometimes there will be some settlement that will push the rods downward, and that will increase pressure. So this type of installation is interesting because it can be quick, but precautions must be taken when you are doing this installation. Here you have a summary. Okay, I talked about this. There's only one, the PWF. I'm not familiar with the PWF. I don't know if we sell a lot of them. The last one, yeah, the PWF2. I'm sorry.
I request this for industrial application. I've done once or twice. It's not something we did that in the past. So should we have to do it again? We can do it, but it's not something common.
Okay. Okay, and finally some frequently asked questions, but just a few of them. Okay, you can read that by yourself, and I covered that, I think, so it's not a big thing.